Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about, what is this? Electric field and electric potential energy. So the examples I will be covering in this video have to deal with that. Let's see. It looks like I'm going to be able to do maybe about 2 examples here. So let's get started. Example 1. Calculate the electric field 1.5 meters from a 2 microcoulomb charge. That's not too bad, essentially. Let's draw a diagram just so we understand what we're doing here. Looks like we have a positive charge. So this guy over here, we're trying to find the electric field at this point. So remember, for a positive charge, the electric field points away from the charge itself. Not that is very relevant to this question, because all we have to do is just do some number crunching. We know that for the electric field, if you don't know already, it is the force acting on the amount of electric force acting per unit of charge. Okay, so if you take the Coulomb's equation, which is K Q over R squared, you divide away one of the Q's, or this is per charge, then you are left with KQ over R squared. So let's put in some numbers. We get 8.99 times 10 to the power of 9, which is the K value. It's the constant that you can find in your data booklet, times 2, which is this charge over here, the charge that we're talking about, times 10 to the power of negative 6 coulombs all over that distance, 1.5 meters. Don't forget to square it, because a lot of students will forget to square that one. Okay, so then putting this to our calculator, I get 7,991 if I use this value for K. So that's going to round to about 2 sig figs to 8.0 times 10 to the power of 3 Newton Coulomb, and we're going to use, say, directly away from the charge, okay? Because remember, for positive charges, electric field points away from that charge. And hey, we just talked about that. It was relevant. Away from charge. And because this electric field here is a vector, we do need to specify the direction of the vector itself. Okay, next up, calculate the force that an electron would experience at this point, and the initial acceleration. Ooh, the space will be a little tight, but we should be able to do it. So first of all, we need to find the force acting on an electron. It's a very typical question, actually. So we know that the force, by definition, is or opposite to that. Since the electric field is, by definition, the amount of force experienced per unit of charge, then the force acting on the charge would be whatever electric field is at that point multiplied by the charge itself is going to give us the total force experienced by that charge. Meaning that the greater the charge, the more force it will experience at any single point in the electric field. So let's do, really, it's just multiplying whatever electric field we got in A with the charge of an electron. The charge of an electron is the elementary charge, 1.6 times 10 to the power of negative 19 coulombs, and the electric field we will use, without rounding, 7,991.1 repeated, etc. Newton per coulomb. And if you take a look at the units units cancel out very nicely as well. So I'm going to take that, multiply by elementary charge. This is going to give me 1.278, and to 2 sig figs, this is going to be 1.3 times 10 to the power of negative 15 newtons toward, this is an electron, so yes, the electron would accelerate towards the positive charge. Towards positive charge. Okay? looks like change, charge. Next step here is to calculate the acceleration. So I'm breaking this in half, and we know that to calculate the acceleration, this is Newton's second law, divide the net force by the mass of the electron is going to give us our acceleration. And the net force, we will use a non-rounded value we found previously, and divide it by the mass of an electron, which we can grab from our data booklet, 9.11 times 10 to the power of negative 31 kilograms. And no, you're not required to memorize that number. Okay, so after I put this in, I get 1.4, rounded to 2 sig figs, 1.4 times 10 to the power of 15 Newton per kilogram, or meters per second. And again, it's going to be towards the charge, okay? Towards positive charge. Running out of space, okay? So there we go. Yeah, interesting how that number here, this is very big in comparison to the amount of force, and that's for the acceleration, and that just has to do with the physical properties versus the actual motion there. So very interesting stuff. Okay, you know what? I changed my mind. I'm actually going to break this video off into 2 parts. So this was just example 1. Stay tuned for example 2 and a whole slew of examples in this lesson. Thank you for watching. Fat Mama Physics signing out.